Howdy folks, in this section here we're going to look at applications involving vector-valued functions, and perhaps the most classic example is to describe motion in 3 space. And so that's what we're going to be doing in this section, and this pre-work is to get us ready for that. So before we get going too far, let's do a quick review of a few of the kinematic facts, or ideas, I guess I should say, that we discussed in Calc 1. And so the easiest way to see the relationship between these two variables is what you were introduced to initially in Calc 1, which was the relationship of these variables through differentiation. So in this case, we're given a position function, s of t, of an object that's in 3 space, where at any point in time t, for t greater than or equal to 0, this output vector gives you the position of the object. So the first thing we're asked to do in this problem is to find the velocity function of this object. And so this requires us to remember that, just like we saw in Calc 1, that the velocity function, and in this case it's a vector value function, is simply the derivative of the position function. So if we go to take the derivative of this position function here, we take the derivative, as we learned in the last section, we take derivatives component-wise when we take derivatives of our vector-valued functions. And so this would be the vector 2e to the 2t, comma 2e to the 2t, comma 4e to the 2t, taking the derivative and applying the chain rule on this. One thing that makes a lot more sense now that we're dealing with vector-valued functions is a distinction between the notions of velocity and speed. So remember that velocity is a vector, and then speed is its magnitude. And this is really nice because the distinction was a little bit harder to see in one-variable calculus, where the only notion of direction we had was a direction moving to the right or to the left. But now, because we can have vectors pointing in any direction in either 2 or 3 space, it makes a lot more sense to distinguish between velocity and speed. So let's go ahead and find the speed function of this vector. And so we just said here that speed is the magnitude of the velocity. And so our speed vector, and we don't have a commonly agreed upon letter for speed. Some people may use s, but I think we're using that for position here. So I'll just say that the speed is equal to the magnitude of v of t. And so if I take the magnitude of this position function, it'll be the square root of each of the components squared and then summed up. So we'd have 2e to the 2t quantity squared plus 2e to the 2t quantity squared plus 4e to the 2t quantity squared. And we could clean that up. Be careful here, folks. When I distribute the square here, I'm squaring each of those constants. When I'm squaring e to the 2t, what I'm really doing is multiplying e to the 2t by e to the 2t, and there I sum up the exponents, which is how I get 4t. So I'm just saying that the reason why this is 4 is different than the reason why this is 4. We can keep cleaning this up, and I believe this comes out to be the square root of 24 e to the 4t, which we could simplify then as 2 square root of 6 e to the 2t. And notice, what's most important to notice is that the velocity is this vector valued function, where the speed is a function at any point in time t. You plug it into this expression here, and it will tell you the length of the corresponding velocity function. So the last example then is to compute the acceleration of this object. And remember here, we just remember that the acceleration, as we saw in Calc 1, the acceleration is simply defined to be the derivative of the velocity function. So that's d dt of v of t. And I'll just compute that component-wise here as 4e to the 2t, comma 4e to the 2t, comma 8e to the 2t. And there's my velocity vector function. Folks, please take a look at the solution that I've written here. It's a little bit cleaner, and I will see you in the next video.